Hello everyone, we will continue with our lecture series. Last class we saw this dynamic programming and we realized that actually it's a very good approach in general in the sense that it gets into this closed form solution of control. However, towards the end of the lecture we also saw that it actually results in this huge computational difficulty and all, which Bellman termed as curse of dimensionality. So, there are ideas there which to kind of avoid that and then get some meaningful solutions at least for limited class of problems actually. So, we will see that in this particular lecture one approach which is called as approximate dynamic programming, and here you will see some sort of a fusion between these two ideas of calculus of variations and dynamic programming actually. Okay. And followed by that we will use those results in this method called adaptive critique, and a variation of that and a little bit computational more efficient sort of ideas there, which is called single network adaptive critique actually. Okay. So, let us get started there. Okay. So, this is the outline of this particular lecture. First, we will study what is approximate dynamic programming, and then we will try to see what is adaptive critique design, okay, followed by the single network adaptive critique, and we will see examples where we will give some comparisons between performance comparison between AC and SNAC. Okay. So, that we will see in 2-3 example problems actually. Okay. So, let us see the first thing first, which is approximate dynamic programming actually. So, everything will happen in discrete time domain here, and the integral will substitute like a summation and things like that actually. So, the objective is still very similar to what you have seen before, and that means to optimize this J, which is a cost function. So find a UK so that you can optimize this actually. In other words, formally speaking, to find an admissible control UK which minimizes this meaningful cost function given this way, but it is also subject to the constraint of system dynamics, which is on the form this way actually. Okay, with appropriate boundary conditions, and this entire class will assume that n tends to infinity, that we are talking about infinite time problems actually. And typically these are when you talk about infinite time, these are typically regulator problems. Okay. So, even though the generic cost function will be used for deriving results and all, most of the examples that will follow will have quadratic cost function actually sitting there. Alright, so we write this first thing is this J, okay, we start from something like Jk. Remember, k starts from 1, then it is J. Or you can define Jk starting from k itself actually, wherever that is, and then n minus 1 actually. Okay. So, we define this cost to go from time Tk is something like Jk. So, then there will be some other variable here, we substitute this k tilde sort of thing, which is the dynamic variable sort of thing, but k tilde varies from k to n minus 1 now. So, this cost function cost to go from time Tk, that is Jk, is written something like that, and obviously if you just take out the first term, that is k tilde equal to k, one term, and then from k plus 1 to n minus 1. Okay. So, this if you just take out at k, then that is nothing but psi k, and then k plus 1 to n minus 1 is nothing but k minus 1, jk plus 1. So, as I told you in the previous lecture, this is something called utility function at time Tk, and this is something called cost to go from time Pk plus 1 actually. Okay. So, like the dynamic programming, we will again define this lambda k as something like del jk by del xk, okay, and then the optimal control equation will be in this form actually. Okay, that we know that del jk by del uk ultimately has to be 0 basically. Okay. Because jk, one of the conditions that needs to be satisfied is a necessary condition that needs to be satisfied is del jk by del uk has to be 0 actually. Okay. So, what is del jk by del uk? If you go back to this jk definition, jk is nothing but this psi k plus jk plus 1. So, I substitute that, and then here I will substitute that. So, jk is nothing but psi k plus jk plus 1. So, this partial derivative del jk by del uk is nothing but this term plus this term actually. This term I will keep it as it is, because psi k is something that I know from this cost function definition and all that. So, that will be a direct derivative sort of thing. So, I will keep it that way. But this del jk plus 1 by del uk, the effect will be felt. That means, jk plus 1 will be perturbed by uk through xk plus 1. That is the system dynamics actually. In other words, if I apply a control uk, that will result in some perturbation in xk plus 1, okay, because our system dynamics is like this, right. If I apply a uk, it will result in some difference in xk plus 1, but jk plus 1 is a function of xk plus 1. Okay. So, because of that, there will be some change in jk plus 1 actually, and that I have to keep it actually. So, how do I keep it? I will keep it through this chain rule of derivative actually. Okay. Remember, these are all vector matrix algebra, so you have to be slightly more careful about writing these chain rules and all that actually. Okay, we have seen some of these partial derivative results, chain rules and all in very beginning lectures, where we reviewed this matrix algebra and things like that actually. You can see some of those if you have forgotten that. So, this del jk plus 1 by del uk, okay, I am writing it as something like partial derivative chain rule sort of thing, write it this way. Okay. Now, what is this? This is nothing but by definition lambda k plus 1. Remember, lambda k is defined as something like this, del jk by del xk. So, lambda k plus 1 is nothing but del jk plus 1 by del xk plus 1. So, that is what is lambda k plus 1. So, ultimately what my equation tells me that this has to be equal to 0, that means this expression has to be equal to 0 finally. Okay. This is my optimal control equation. However, how do I get this lambda k plus 1? That's the bottom line actually. So, for doing that, we need to go back to the other side of the story, that is the co-state equation sort of thing. Okay. And as I told, this part can be evaluated from system dynamics actually, this particular term, and this will be directly evaluated. Okay. So, coming back to this co-state equation, this remember this is a definition of lambda k is nothing but del jk by del xk. Now, that is equal to this del psi k by del xk plus this term del jk plus 1 by del xk sort of thing. Okay. Now, remember this particular thing, okay. Now, psi k is a function of xk and uk both. So, this particular thing first of all is a direct function of xk. So, okay, in a given example, I mean typically it is a quadratic cost function. So, let me give something like psi k. Psi k is nothing but xk transpose qk r xk plus uk transpose rk uk, in that kind of thing. Okay, and some people put half actually. So, let me put that. Okay. Okay. If you see that way. Okay. However, remember that our control uk is also a function of xk. That is what we ultimately want actually. Okay. Some function phi of xk actually. Okay. So, what is happening here? Del psi k by del xk plus this term, but this particular term del psi k by del xk, okay, what you are interpreting is psi k is a function of state and control both. Okay. So, one thing is direct function, direct partial derivative I can take it. The second one is, because control is going to be a function of state, I will also account for that and write this chain rule actually. Okay. So, the first term is direct, the second term is this one. Similarly, this term when I talk actually, this term will be first actually jk plus 1 is a function of xk plus 1. So, this entire thing what you see here, okay, whatever you see here is nothing but del xk plus 1 divided by del xk. Okay. This del xk, this particular term, okay, this term what I see here, okay, this entire term, okay, is nothing but this del xk plus 1 by del xk transpose actually. Okay. So, this is again the chain rule of this term, this del xk plus 1 by del xk, this term, okay, and this term taken together is nothing but that actually. Okay. But this particular term again is one thing is okay, remember this xk plus 1, okay, we just saw that xk plus 1, oh, okay, 1 second. Okay, xk plus 1 is nothing but f of xk uk. Okay. Alright, so that is again a function of xk and uk both actually. So, we keep all those things in mind and write, okay, this particular term what you see here, one term is direct, okay, because it is directly a function of xk, and the other term is through uk, but uk is also a function of xk. Okay. So, this is what is kept here actually. Okay. So, just this is a little bit tricky derivation, I understand that, but just follow a little bit bookkeeping here actually. First thing is this is just from definition, and this term we clearly explain that this is one is direct, the other one is through u basically. Here also similarly this jk plus 1 by xk, remember xk plus 1 will also be perturbed the moment you perturb xk. So, because of that this is non-zero, that means this one comes directly from xk plus 1 perturbation actually. So, I write it as something like this term del xk plus 1 by del xk transpose times this one, but this particular one you can realize that this is a function of this xk plus 1 is a function of both xk and uk is a function of xk again actually. Okay. So, this particular term is because of that, first is directly, then the second one is through uk basically. Okay. And I understand there is a small little bit abuse of notation here, but I think because all partial derivative I am writing it the similar notation sort of thing, but let us ignore that for a second actually. As long as you understand what you are doing is fine actually. So, all these partial derivatives are expanded this way actually. Now, once I do that I can think about reorganizing the terms and all that here. Remember this is nothing but lambda k plus 1 actually. So, what I do I will take the first term here and first term here, and remember this transpose will nothing but this transpose plus this transpose, which is something like this transpose into this transpose actually. A B whole transpose is nothing but B transpose A transpose, you can do that actually. Anyway, so the first term here and first term here and lambda k plus 1 from here. So, I will keep it this way. Then the second term you can see that del uk by del xk transpose is common here, and this will be this transpose is also in the left hand side actually, that will come after expansion. So, both of the terms will be in the left hand side. I will take out this as common and write it that way. Okay. So, my lambda k is actually theoretically speaking is actually this big expression here actually. There is a transpose here by the way. Okay. Let me probably this got hidden. So, let me write it this. Okay. This is there is a transpose here. Okay. Alright. So, this is what it is. However, if we can see that this equation on the optimal path, this equation is also valid. This is nothing but 0 actually. Okay. So, what we do here is if I put it there, this entire expression becomes 0 actually. So, that means if I am worried about only optimal path, then my lambda k is nothing but only the first term actually. Okay. This is what it is. Okay. So, this is a recursive equation sort of thing. That means, if I know lambda k plus 1, I can know lambda k. And typically from boundary condition we know this lambda n actually, and even if it is a finite time problem and all that, we know lambda n is del phi by del x n and all that that way. So, we start from there, and this actually tells us there is a backward recursive equation sort of thing. And also remember in 2-point boundary value problem calculus of variation approach, we actually have lambda dot equation, but lambda dot is typically propagated backwards actually. Okay. So, all these are compatible actually that way. Okay. So, what is the summary? Summary of necessary conditions is something like that. State equation is available to us. Then the co-state equation is something like this. Okay. Remember, these are all functions of state and control xk and uk, and obviously lambda k plus 1 also here. So, I can write it as lambda k is some function of xk uk and lambda k plus 1 as well. And optimal control is ultimately a function of this one xk lambda k plus 1. Remember, this is the equation. This is the equation. If I solve for uk from here, ultimately this is going to be a function of xk and lambda k plus 1 actually. Okay. Remember, xk plus 1 will be substituted by that f of xk uk. So, that means what you get here is just a function of xk uk only basically. Okay. So, ultimately this optimal control equation can be written something like that. So, essentially the boundary conditions are also split. So, what you see observe here is we actually landed up with something similar to what we knew earlier in calculus of variation approach actually. Okay. So, you have state equation, co-state equation, optimal control and boundary condition. That is what it was a calculus of variation approach actually. However, we started with something like this utility function and all that actually, cost to go and things like that. So, these are the concepts coming from dynamic programming actually. Okay. And these are all happening in discrete domains. So, obviously, these are some approximations involved and all that actually. So, that is why it is approximate dynamic programming actually. Okay. Some references, if you want to see some of these derivations a little more carefully and all, you can see this reference, which is very standard nowadays. It is actually a chapter written in a handbook, Okay, the handbook is written for intelligent control in 92, about 20 years back actually. Okay. But there is a nice chapter here which talks about approximate dynamic programming actually. Okay. And you can see our paper also where these derivations are summarized again actually. So that's one thing. But this paper will talk about more on what we are going to do next in the adaptive critique and single network adaptive critique and all that actually. Okay. Alright, so this adaptive critique design for infinite time regulator problems, let us see that one first. Then we will talk about SNSE as in some sort of a extension of that actually. Okay. So, now here I assume that you have some little bit idea of neural networks and if you do not have much of ideas, then nothing to worry so much. There are toolboxes available in MATLAB and other softwares and all that, where neural network training algorithms are available to experiment actually. Okay. And again, what is neural network training? You can think about neural network as something like a function approximation black box sort of thing, where if given some sort of input, you get some sort of output. But if your weights are selected properly, then you will get proper output given a set of input actually. And how do you get this weights adjusted properly? That requires some sort of training. And then that's a different ball game altogether. There are various kinds of training available and all that. What you are interested here is a very standard backpropagation supervised learning, supervised training. It essentially tells us that if my the whole idea here is I can explain a little bit here. Let me talk about something like some function of x and a bunch of weights actually, let's say. Okay. Then x is known to me because that's the input, but w is something not known to me actually. Now what I think, what is the problem? Problem is this is the actual output that I am getting from here after selecting a set of w's and all that. Little more explanation. I can think about w. Y equal to something like w3. Let's say there is a reason for that. W3 transpose something like phi 3 of x if I write it, where phi 3 is a set of basis functions which I select. So I know about that actually. Then I will do something like I will take phi 2. Okay. Then I will multiply with w2 transpose. And then I will take entire thing something like a phi 1, okay, and then what I do is I write something like w1 transpose, and this series can continue actually. Let me stop here because it is sufficient to do actually this much only. So this is my y actually. So what I am getting here is all these phi 3, phi 2 and phi 1, these are defined functions actually, predefined functions typically taken as sigmoid function, tangent sigmoid, things like that. Whereas w1, w2, w3 are unknown parameters to be fixed, and it needs to be fixed in such a way that given my set of x, whatever my input variable, my output variable should match that actually. Okay, so for that let's say we require some sort of a training data. That means sorry. Okay, that means what I am telling here is let's say this y, okay, what I am telling y should be y star like that actually. Okay. That means if it's not y star to begin with, but if my weights are selected properly, then y will behave like y star actually. So obviously there is an error delta y which is y minus y star. Okay. And what I am doing here is I want to select kind of minimize a cost function, error cost function, let's say something like half of delta y transpose delta y actually. Okay. So this is actually a function of all these weights, the weights w1, w2, w3. So what is done here typically is del E by del w1, okay, equal to 0, del E by del w2 equal to 0, okay. Okay, this is also del E by del w3 equal to 0, like that. So if you put it and then go through this chain rule of derivatives and all that, you will be able to come up with some sort of necessary conditions. And typically this optimization is carried out in some sort of numerical optimization sense actually. That means these closed form solutions are typically difficult to get. Okay. So this equations, even though we know, we don't put it. Okay. So we try to directly start with some sort of initial guess values and then try to update the sequential update sort of thing, which will lead to this error minimization actually. That means your y, actual y will converge to y star. It will behave in the like a desired output in the trained domain, wherever in the domain that is selected for training, within that domain it is so going to mimic like that actually. That's the whole idea of neural network synthesis, training and all that actually. If interested, you can see many books available for neural networks actually. Okay. Now coming back, what it tells us that if presented with proper input output data, okay, and that proper is again you have to really do a careful job to provide a proper training data basically. Then what it tells us that there are training algorithms, essentially error minimization algorithms, they exist so that after training the network can capture the underlying functional relationship. Okay, these are not number fitting, these are function fitting actually. That means once the function is fit actually, then given a different data, remember x are a bunch of numbers now actually. So if you have fed a bunch of numbers and you got some y star and you have trained the network in such a way that delta y is minimum actually. That means these weights are selected in such a way that delta y is minimum. So that means the functional relationship is captured. So in other words, if I present a different set of input state x actually, whatever that is, then I will again get some sort of a similar output that I would have otherwise got actually using all these optimality, I mean all these ideal conditions what I mean actually. Okay. So this is the idea of neural networks. So, and then there is a theorem which also tells us that a 3-layer network with sufficient number of hidden layers can approximate any continuous function within arbitrarily small error bound in compact set obviously. Okay. So set has to be kind of closed and bounded and all that actually. Yes, so, okay. Okay, let me complete that. Okay, in compact set. All right. Okay. So this is what the basic knowledge that we want. That's all actually. Means there is a neural network which can approximate some underlying function. There are training algorithms that exist which can do the job for us. Okay, and there is also a powerful theorem which tells us that only a 3-layer network, something like this, can approximate any continuous function. Okay, that is more important actually. Okay, so that means there is some degree of theoretical guaranteed thing that comes along actually, but still so also remember the way of selecting these W's, the weighting matrix dimensions and the function selections and all that are still art actually. That means there is no clear cut theory which will tell you what kind of functions that you need to select for phi 1, phi 2, phi 3, and it will not also tell you what the dimension of that. That means what the number of functions, basis functions and weights that you want to select in each layer. These are still subject to kind of open question basically, but normally it turns out that actually not a very large network, it is about 4-5 hidden layer neurons that will do the job actually. Okay. Now with this background, what is adaptive critic methodology? Let us say this is the methodology which tells us that let me now assume a neural network which I call it as action network. For all that it will do is, given a set of state xk, it will predict my uk. That is my ultimate objective. Remember, now if y is my uk here, y is u, then I have got a closed form solution for control basically. Okay, just imagine that this y is essentially, okay, this y is essentially my u function. Okay, this is my u. Okay. So what I got, okay, what I got is actually a control which is a state feedback form actually. Okay, so this is what I do actually there. Okay. However, to get that, okay, there is a necessity of knowing lambdas and all that, and the information that we have is only xk. Okay, so there is a necessity of another network which we call as critic network, which will do nothing but predicting lambda k actually. Okay, that means this network's job is to predict an optimal lambda k knowing xk, and this network's job is to predict an optimal control uk knowing xk. So ultimately, this is the network that we are interested in. Okay. But on the way we need this also, and there is an interaction that will go on actually. That means while training action network, we will assume that critic network is optimal, and while training critic network, we will assume that action network is optimal, and that has to be some sort of cycle training and all that. And ultimately, if everything converges, then we will tell that okay, this network that is converged here is nothing but my optimal control solution actually UK. This is what it tells you. Finally, this section network leads to this optimal control solution, but that will happen only after mutually consistent training of both the networks. Okay. What are the advantages of this method? Before you see the actual steps and all that, this is applicable to for nonlinear problems in general without any linear or quasi-linear approximation of the system dynamics. You can directly take the system dynamics as it is actually. It is also solutions for a large number of initial conditions. What you are looking for is some sort of a semi-global solution and all that. Wherever the network is trained in that domain, it will operate something like an optimal controller actually. Okay. We are getting a closed form solution. Remember that this expression what we saw here actually a closed form solution in a way. But this will happen to be a closed form solution only within the domain of training. Okay. Wherever you have trained the network, within that domain, this relationship is valid actually. Okay. So, because of that, we can interpret that as some sort of a semi-global solution and all that, because the domain can be expanded as we like actually, at least theoretically. Yeah. So, you are getting something like a feedback optimal control in the domain of interest. Okay. That's the advantage actually. This is something like a feasible computational load, even though problem dimension increases and your control application duration increases and all that actually. Still, it is not like infeasible computational load like dynamic programming. You still need some time, couple of hours probably to train the network, depending on the computer first and then software that you are using and all that. Still need computational thing of the order of minutes and hours probably, but not like infinite infeasible computational load. For example, if you really use these classical techniques for dynamic programming, for a particular aerospace guidance problem, it takes about some 20-22 years altogether actually. So, that is not, we are not talking like that actually. Okay. Still minutes and hours, but still it is feasible actually. Then it is a self-contained methodology. It does not talk about some other method, solve it and then just train the network. So, it does not talk about that, it is a methodology by itself actually. Okay. Ultimately, it leads to real-time control, because what you are getting is control as a closed form solution finally. So, it is given as after the training process is over, you have got the optimized weights already. So, what you are doing here is just simply evaluating this function u as a function of state actually. Okay. Now, the question is how do you do that? So, first thing is let us see how do you synthesize the action networks. By synthesis what I mean is how do you come up with the desired values of the output actually. Okay. Remember, action network takes sk as input and gives uk as output, but this training process demands that you have a corresponding uk star, which is the desired value of uk actually. Okay. So, how do you get that there? So, let us take it through, and the results that we have is state equation, optimal control and co-state equation, you know that actually. Okay. So, we give some, we assume certain network with some initialized weights and all that actually. So, we get some sort of a UK. Okay. And by the way, this initialization does matter, and I will talk about a process of good initialization also actually. But anyways, after initialization, this xk, if I feed it to the network, I will get UK. And now that I have got xk and uk, I have got, I can feed that into state equation, and hence I will get xk plus 1. And if I get xk plus 1, remember I am assuming that critic network is optimal here. So, this using this optimized critic network, I will get lambda k plus 1. Okay. Now that I have got lambda k plus 1 and xk also available with me, I can feed it both lambda k plus 1 and xk in the optimal control equation, and I will get uk star actually. Okay. Now, given this input, this should be my output, or this is my actual output. So, there is an error between the two. So, using this error minimization algorithms and all, I can adjust the weights. That's my training actually. So, this training process continues like this. Okay, and remember, this is, even though it can be a single point, but ideally speaking, we typically do this. This batch processing sort of thing. That means you take a set of state vectors, that means let us say 100 states together. 100 states means let us say the system has x1, x2, x3, then the value for x1, x2, x3 selected 100 times actually, okay, from the domain. So, we have 100 things like that and 100 outputs like that. So, we have this batch training algorithm, where the cost function accounts for error in the each component of the actually. Okay. So, the idea here is if you do that batch processing, the local minimum trapping possibility is minimum actually. Okay. So, that is why you do that, but I think for each of the state that you take, you will get each corresponding UK star actually that way. So, you have this error and then try to optimize these weights based on that information actually. So, that is external network training. What about critic network training? Okay. This critic network training will talk about something like this. We have this xk, I mean gives you lambda k, but we need to get a lambda k star, it's a desired lambda k. Okay. So, how do you do that? This is like this, you got xk, you can also feed that in the external network, which we assume is already optimal, then you get some sort of optimal control UK. Now, xk and UK is available, so we got xk plus 1. And remember this, there are two assumptions here. One is external network is optimal, and critic network that you are going to train for the Tk is also assumed to be optimal at Tk plus 1. The reason being, finally, my boundary condition is known for lambda n is actually a function of xn. Okay. So, that means, I know a final condition actually from the boundary condition sense actually. So, I can assume that my future time, my critic network is already optimal actually, and in fact, it that entire observation gives us some sort of a training approach for critic network actually. In other words, for finite time problems, we will like to train the network first using this boundary condition and then proceed backwards actually. For infinite time problems, lambda final value of lambda happens to be 0. So, we train it in the domain of very close to 0 and all that actually, and then try to enlarge the bound and all that way. Okay. But anyway, coming back, what it means is the critic network is already optimal at Tk plus 1. So, that means if I feed it, I will get a lambda k plus 1 also. Now, I got xk and lambda k plus 1. So, using co-state equation, I will get it desired lambda, and again I can train this based on this error value between the two actually. Alright, so this is the procedure. If I train external network, assuming critic network is optimal and the vice versa, but also remember these are on the way we are using state equation, optimal control equation as well as co-state equation. So, all the three equations are getting used, and hence after mutually consistent training, we will get this optimal control basically. How do you initialize the network? As I told, that is also important. And for initialization, this is what standard method that we propose, that okay, you linearize the problem first and formulate something like a problem in the linear domain actually. That means, you have this formulate a, so there is a small error here, formulate a rather not lumped per se, it is LQR problem, okay, for linear quadratic regulator problem, okay, because your cost state equation becomes linear and cost function is quadratic. So, it is LQR problem, and obtain the LQR solution for that. This solution will tell us this is our standard result coming from Riccati equation and things like that. As the discrete optimal control solution, I mean that is also one lecture I have already covered actually, you can see that if you want. So, lambda k is SD into xk and uk is minus kd into xk, where SD and kd are available from this LQR solution. So, by solving this Riccati equation and all that actually. So, now because these relationships are available, you can actually train the networks using these relationships, that is called pre-training actually. So, you start with very arbitrary set of weights, but then first you train the network so that the networks can mimic this relationship at least. That means, they are actually mimicking this or they are actually predicting this optimal control relationships for linearized version of the problem actually. Okay. So, that actually gives us some sort of a good initialization, so that the nonlinear problem training can happen quickly actually. Okay. Another alternative ideas also exist, that you can also obtain some sort of a control solution from other techniques, let us say using dynamic inversion. Then for a known state, assume that this solution is already optimal, even though it is really not optimal, and then you can compute the associated co-state. But this is a tricky thing here, because remember the control is actually a lesser dimension, but the co-state is actually a higher dimension actually. So, you will invoke some sort of a pseudo inverse and all that, where I personally sometimes do not like actually. If the dimensional discrepancy is high, when you have one control and let us say in 8-9 states, then obviously this is not a good approach actually. Okay. But if it is something of compatible dimension, it is a 3 states 3 control, or probably something like 3 states 2 control like that, then you can use this actually probably. But the advantage here is you are not using this linearization technique, you are not linearizing the problem actually. Okay. Already. So, if you do that, then you can train the networks based on these control and co-state solutions, which you can use it actually for actual training. So, this is the idea of adaptive critic, but on the way, as I told, we also have this idea of single network adaptive critic. Okay. So, what happens here is, if you go back to this approach, this idea here, there are actually two networks. So, essentially it is something like okay, I forgot to tell you that okay, this training procedure that you are talking, action and critic, you first you train the action, assuming critic network is optimal, then you go to train the critic network, assuming action is optimal. But what you are doing here? You are assuming critic is optimal and you are changing this actually. So, what you are telling here is this action network is not yet fully trained, partially trained, let us say, but using this I am actually training the co-state equation. But once I train the critic networks, I have actually changed this network already here. So, there is a necessity of retraining the action network again. And once I do that, whatever action network I assumed in the critic network training here is already trained. So, I again have to come back to critic network and train actually. So, this process of what you are seeing here, action network training and critic network training, this needs to be mutually consistent. That means, you come once you train critic network, go back to action network, train that again, then once you are done with that, come back to the critic network and train it again. Once you are done, go back to that and then train it again, like that actually. And after a while, you will find that no further training is necessary in either of the cycle, and that is where we call that the mutually consistent training has happened actually. Okay. So, that is called cycle training sort of thing. So, the observation here is the cycle training is necessary because this two network structure basically. Now, can we get rid of that? Because cycle training is typically, first of all, it is computationally intensive. Second thing, there is a possibility of misguiding actually. In other words, if one network goes where, the other one will also go where actually. So, here the idea comes something like this. It can be done provided the critic network is actually remodify. I mean, kind of instead of assuming lambda k as output, what about assuming lambda k plus 1 as output rather? Okay. Then let us interpret what is going on and see what is going on actually. And the assumption here is most of the time, as we seen in like derivations and then derivation of approximate dynamic programming and all, your uk is going to be a function of xk and lambda k plus 1. So, all that I need is uk is something like a explicit closed form solution in the form of xk and lambda k plus 1, which is typically true for most of the cases actually. Now, once that is there, then what it tells us is okay, if I just use a network, one single network, which will give me xk as a function of, I mean lambda k plus 1 as a function of xk, then if I know xk, I know lambda k plus 1, and I know the optimal control solution as some sort of like a explicit solution symbolically available as a function of these two variables, and hence I am done actually. Okay. So, this is what it is, and so the advantages are like this. It retains all the advantages of adaptive critic, it eliminates the action network, and hence it also eliminates the iterative training between action and critic networks actually. So, these are the advantages which saves us lot of training time actually in a way. It also eliminates some of these approximations involved from critic network. Anytime you have a network which is a function approximation, that approximation error is also gone by eliminating that actually. And it also leads us this consistency, the quick training sort of ideas and all that way. So, that is single network adaptive critic. So, how it is done? Let us go back to the structure again. So, we have xk, we have a critic network to train. So, we have got lambda k plus 1. All that you are assuming here is critic network is optimal at tk plus 1 while you are training for tk. So, I am xk, I will get lambda k plus 1. Once I use this xk and lambda k plus 1 in optimal control, I will get uk. And now that xk and uk is available, I will use it in state equation and get xk plus 1. And because I am my xk plus 1 is available, I can use it in critic network to get lambda k plus 2 rather. And because xk plus 1 and lambda k plus 2 is available, I can put it in a co-state equation and get lambda k plus 1 actually. Okay. So, what I am getting here is this is the desired lambda k plus 1 and this is my actual lambda k plus 1. So, the difference between that is error, and based on that I will minimize that to train this network actually. Okay. So, remember this optimal control, state equation and co-state equation, all the three equations are used in the single structure basically there. That results in simplified algorithm, programming becomes simple, the training time saves and all sort of things actually. Okay. How do you initialize? Remember the LQR solution can give us only this, lambda k is some escape, it is not a lambda k plus 1 is not available. So, how do you do that? But we know that this is also available, so and hence we can construct it. That means lambda k plus 1 is nothing but this is a constant matrix SD into a k plus 1, but xk plus 1 you can substitute the state equation, linearized state equation, uk you can substitute back as a function of xk, and hence you will get something like lambda k plus 1 is a function of xk. So, using this relationship you can pretend the networks and then go for the training actually. So, now for rest of the time I'll talk about some 2-3 example problems and give you some sort of a comparison study to see where performance improvement happens. Remember, the result wise it will not vary much if you do consistent training actually, okay, but other things will matter. Okay. Also remember this because of this assumption that this lambda k plus 1 critic network is already optimal at tk plus 1 that you are repeatedly using, and for that there is a necessity of the cycle training, I mean this telescopic training and all that actually. So, what it means is okay, let me pictorially represent that. Suppose you talk about a domain of training, that means we know that our state, let us say some sort of a scalar example, this is my time and this is my x actually. My x is going to vary, but is going to vary within that actually, no matter what, wherever the initial condition it will vary, but it will vary within that actually. So, this is the assumption actually, whatever that. So, then I do not have to worry about the outside this bound and all that. However, what I need to do is, I mean this is my total training data, then what I need to do here is okay, something like this. Okay. Even though I know that this is my x max and this is my x mean, okay, then what I do is I will just slice this thing with a small domain first actually. I will train this network in that domain, because close to the 0 line my pre-trained thing which is linearized expression and all are valid actually. So, I will train this. Once it is done, I will expand this zone a little bit more. Once it is done, I will expand this little more, and once it is done, I will expand it a little more actually. Okay. So, this is initially starting with this domain, then starting with that, then going to that and things like that. This is called telescopic training actually. And while you enlarge the domain, there is a reason for not forgetting also. That means, even if you talk about some sort of a full domain, let us say, okay, this you are generating something like 1000 data points from there, then about 10% I will still recommend that you keep on generating from here explicitly basically. That means, this larger bound should be 900, then this smaller bound should be 100 actually. Okay. The reason for that is the error of the larger values should not eat away the error between the smaller values actually. Okay. So, it means you should not forget the relationship close to 0 basically, that is the whole idea there. That this idea is called telescopic training actually, which is invariably helpful. So, all that is there. So, there is a comparison study sort of thing, you know, this adaptive critic operates in this kind of idea. You have action training, you have critic training, there is cycle training involved and things like that. Whereas, single network adaptive critic does not talk about that, it just trains in one single iteration sort of thing actually. There is no cycle training involved, because there is no action networks per se actually. Okay. There is only one set of networks there. So, we will talk about 3 problems here. One is a standard scalar, same scalar problem that we discussed in the previous lecture. The other one is a 2-dimensional thing, okay, 2 states actually. This is a first order equation, this is a second order equation. Again a very standard benchmark problem, van der Waals oscillator. There are reasons for that. This actually goes for limit cycle oscillations, and hence the control, if the control is not good, you will not be able to regulate the system. You will not be able to drive the states towards 0 basically. Then I will extend that to a little more practical problem, which talks about a third order system, coupled third order system, which is a MEMS problem, micro electromechanical system. It is electrostatic actuator sort of thing. Alright, so first problem first, this is a, okay, for all these things, what we have done is a little bit older computer and all, that needs to be same for all the exercise for a fair comparison. We use something like a Pentium 3 processor with a little less, I mean 930 megahertz speed sort of thing. RAM was less, 320 only. Software used was MATLAB version 5.2. Now versions are quite advanced. It is almost like MATLAB 2012 is available actually. But anyway, that's not the point. Neural network toolbox is also improving, but the exercise is carried out with a toolbox version 3.0 actually. Okay. And training algorithm used is something called LM algorithm, which is very standard in neural network techniques. Kind of the most powerful algorithm that exists in the network training domain actually. Okay. And the number of runs per averaging is 10. So, also remember when you run this algorithm, there are other processing things also goes on there. So, what you are doing here is kind of taking the run 10 times and then trying kind of averaging out actually. So, it will smooth out some of the relationship there actually. It will smooth out some of the noisy relations, very less fluctuation, but it will actually smooth out that part also basically in a way. So, this is the scalar problem. You have the standard equation, you have a standard cost function also, Q and R equal to 1 1, then this is the cost function, this is the solution that we have derived in the previous lecture also. This is the benchmark problem because of the availability of closed form solution, and hence you can compare your results with that actually. So, we have first thing is discretize the state equation using Euler integration of formula, discretize the cost equation as well, discretize the cost function as well, and the cost state equation can be derived using this approximate dynamic programming results like this. And optimal control equation turns out to be like that. Remember, Q and R are both 1 here actually. So, the network structures that is chosen is 141, 141 here, adaptive critic, here it is 141. The convergence criteria selected is something like 1%, but here you have to select for 2 networks, and the cycle convergence also you need to select, that was selected very small actually. Remember, this is 0.02% and things like that actually. It is not percentage per se. This is the absolute value here. Okay. So, these are percentage errors, but this is absolute values actually. So, you have selected something like this, but this is actually not needed here because there is no cycle training here. Wherever things are needed, these are made compatible actually. So, result wise you see both results, this is adaptive critic results compared with closed form solution, which is very close to each other. So, adaptive critic is working. SNSE which is also working, is also very close to the closed form solution. So, the point here is both are working, it is not the, but okay, the control solution is also you can see that both are happening to be fairly close to the closed form solution actually. So, both are happening, that is not a problem, but what is advantage in SNSE is time actually. So, let us see what happens here. See the computational time sense, you can see that number of iteration, that means the cycle training sort of things and all. It talks about some time of computation and all that. Wherever SNSE talks about only iterations like this. See what you see here 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 iterations if this algorithm is supposed to converge actually. Then you go to the second iteration and third iteration like that actually. Here is not needed. So, what is done here is simply 8 iterations here and you are done actually. Okay. So, essentially if you see all this ultimately the time to train is what matters actually. Okay. And finally, if you see the total time taken for all these, you add up all that, you will get it something like total time here, and here the total time is something like this. So, essentially it turns out that time of training is essentially 43% of adaptive critic in SNSE. So, that is roughly kind of 40% you can say, which is a lot of advantage for bigger problems actually. Okay. Now, cost function sense. For each of the initial condition, you can actually evaluate the cost function and plot it, and then the claim here is again cost functions are fairly similar to each other actually. So, what you are claiming here, both will work, but SNSE will work slightly better in the sense of computational advantage actually primarily, and it will also eliminate your other programming difficulties and then small approximation errors also and things like that actually. Coming to the second problem, this is a Vanderpool oscillator. Again, we will talk about a quadratic cost function and things like that. Cost function is discretized. Okay. State equation, remember, is a two-state problem now. So, this is also discretized and written in the form of Euler integration. Co-state equation can be derived from the standard co-state equation that we discussed about. Okay, optimal control is like this. So, using this thing, we will formulate this for problem. Okay. And then again the selection criterion has to be selected properly. So, critic network, action network, and then the 5% error here, and then absolute values of error, the cycle training is something like this. And wherever these things are compatible, wherever things possible, we need to be compatible. So, the critic network here is 262 structure, it is also 262 structure, and convergence criterion here is 5%, here is also 5% actually. Okay. And also there is one point to note here that my own experience, I will recommend something like a breakup network actually. In other words, even though this critic network can be actually theoretically solved in terms of single network really, but because there are 2 outputs involved, I will rather prefer to have 2 sub networks, which one sub network is 261 and otherwise 261 also. And then I will consider that the entire structure is something like a single network actually, but that is my own preference, it need not be like that always actually. So, this is like this and then it once you do the comparison study, the Q and R are selected that way, and here there is a cycle training ideas there, telescopic training ideas. First you train with a smaller domain, then enlarge it and things like that. Okay. So, this first is 5% of the total domain, and then subsequently it is increased by 5% and all that actually. So, again you can see because there is no closed form solution, we cannot compare individually, but comparison with respect to SC and adaptive critic and SNSC is always possible. So, we train both those things, both ways we solve and then plot it together for different initial conditions and all that actually. So, you can see that position and velocity both are given to 0, and remember this is a limit cycle problem. In other words, if control is not 0, for any non-zero initial condition, you will never be able to go towards 0 condition. Okay, you will never be able to drive the states towards 0. It will go towards the limit cycle. And what is limit cycle, by the way? Those of you who don't know, you can see this. If I plot a phase plot, that means x versus x dot. Okay, what I am looking for is starting from something I will go to 0 actually. That is not happening. So, this is something like a closed loop function sort of thing, and this is happens to be stable limit cycle. That means, if I start with anything I will merge into the limit cycle and then continue oscillating in the limit cycle actually. But ideally speaking, if I start somewhere, I want to go to 0 actually. That is not going to happen unless my control is good actually. Okay. So, that is the problem here. Alright. So, this is what it is. They both are working. However, comparison sense, performance comparison sense, you can see that the time taken is invariably half actually. Pictorially it is put in a bar chart sort of thing. Okay. So, telescopic training time, if you see that, then the training time turns out to be half actually. And total training time, if you see, it's believe it or not, exactly is 43% it turn out to be. Okay. So, the claim here is it is going to be slightly lesser than about 50% or roughly about 50% of the time will be done actually. Cost function comparison, again both happens to be similar. So, that is not much of a concern, but to make adaptive critic work, you really need to be lot more careful in your programming and all that compared to SNSC. Okay. So, that is another big advantage looking from simplicity of the structure point of view actually. So, finally, this is the electrostatic actuator problem. Okay. This is the system dynamics is something like this. There is a mechanical part which oscillates and there is a charge part which is electrical actually. Okay. So, what is the objective here is actually to maintain some sort of a gap. G stands for gap actually. Okay. There are two, I think I have a picture somewhere. Okay. Here G stands for this. Okay. So, this gap needs to be maintained at a particular value of G naught actually. Okay. So, this is a control input is your control voltage actually. Okay. V in is your control input. So, this V input has to be manipulated in such a way that G has to be maintained at a particular separation G naught actually. Okay. The system, okay, this is your spring mass damper, this is a spring and this is a damper, this is a mass which oscillates actually, there is a fixed plate, okay, and this this gap is controlled by driving this voltage input actually, okay, and there is a resistor involved here which will have a current flow and things like that way. Yeah. Alright, so this is what it is. This is the system dynamics, and then the cost function is something like this, which needs to be minimized. Okay, what is x? That needs to be thought about actually. X is your state, but that state I will derive it now. I mean, I will tell you now what's the state actually. State has to be deviation state actually. So that means G is not the state, even though the dynamics is given in terms of G, but what you are considering is the difference actually. G minus G naught happens to be the state, one state actually. Okay, that we will see that. I will show you that actually. Also, the cost function also in the discretized form, something like this. Okay. So, ultimately what you need is your state equation, we write it in a state space form. So, we define this Z1, Z2, Z3 sort of thing, these are the states Q, G and Z dot, and then we write control V as something like V input and write this equation. These state equations will be given in the form of this Z1 dot, Z2 dot, Z3 dot or function of Z1, Z2, Z3 as well as control input actually V in. Okay. So, this is what we want to see in any given control synthesis problem. We want to see it in the form of state space equation actually. So, we wrote that in a state space equation, but now remember there is a necessity of finding out the equilibrium states actually. Okay. So, for that we need this problem has all these parameter values given something like this. Okay. And then at equilibrium point what will happen? You consider this okay. Remember Z2 is the G. And G is a desired value is given to us actually. Okay, so that is what you put it as. Okay, and then make sure that the equilibrium point condition Z dot is 0 That means all the derivatives would be 0 actually. Okay. And V2 is I mean this Z2 is 0.5, that is the desired value that we have. So, we put 0.5 here, okay, whatever Z2. There are 3 equations now in terms of 3 unknown variables, and what are the unknown variables? Z1, Z3 and V. So, Z3 is 0, okay, so that is 0, Z2 is already there, okay. And Z1 can be solved from this equation, so that is already available actually. And once you have Z1, then you put it back here and try to solve, the Z1 has to be solved from this equation, okay, and this turns out to be something like that. And once you have Z1, you put that equation in the first equation and solve for V actually. So, that will give you the corresponding V naught. So, this is the desired value of state at the operating point or equilibrium point, and this is the associated control value at that particular point actually. So, now that the desired states and control both are available, we can formulate the deviation dynamics, and for that we define x as the deviation state, this z minus z naught, and u is the deviation control, which is v minus v naught actually. So, with that definition, we can rewrite the system dynamics as something like this actually. So, these are all happening in the form of deviation states and deviation control now basically. So, this is a standard regulator problem now. So, and hence we can select this cost function, quadratic and things like that actually that way. Remember, the cost function was given in the form of x actually, not in the form of z, and this x is deviation state and this u is deviation control actually. Okay. Alright, so this is what it is, and this is the deviation state. So, now we are ready. So, the cost function is a state equation discretized and corresponding co-state equation is derived, optimal control is also derived. Okay. Again the two structures needs to be compatible. So, compatibility is maintained actually. The weightings are taken 1 and again the comparison result sense time domain simulation both happens to be similar, and hence both are both work actually. Okay. So, I do not claim that one works better than the other. In fact, if theoretically speaking, if training is consistent, AC is nothing but SNAC and vice versa actually. So, both the results are compatible. Similarly, if you see these are two states, this is charge and Q, and then the position V2. Okay, this position is Z2 basically. Okay. So, what you are getting is charge Q and position Z2, and then Z3 and then control actually. Remember this, after you solve this, you can actually recompute your original state, because the definitions are already here. Okay. So, once I get x and u, I can recompute my z and v actually. Z is nothing but z naught plus x and v is nothing but u plus v, u plus v naught. So, I compute this v rather, okay, and the corresponding z will be available actually from there. Okay. But you can also think about doing it other way around. You just simply compute v, u equal to, this v equal to u plus v naught, then you have z naught initial condition. So, you have the original system dynamics. Okay. This original system dynamics can be simulated directly actually. This system dynamics, once you have control and initial condition, you can simulate the system dynamics and validate your equation from the nonlinear system point of view actually. So, that is what is done here. Okay. So, this is all that is done, and it is happening, it is working together, and computational point of view, it is happening in an efficient way. It is very close to 43%, now it is 44% actually. So, little less than half of the time will be done, and your simplicity will be maintained, that is more important actually. Okay. The cost function evaluation sense, both are again equivalent actually, no, not much actually. So, conclusions about SNAC, SNAC retains all good features of adaptive critique, it eliminates the action network, and hence it eliminates the approximation error due to action network, and also there is no necessity of iterative training loops between action and critique networks. Computationally it is simpler, and hence writing the program and all that also becomes simpler, and it essentially leads to a significant amount of computational savings actually. Okay. Little more than half actually, but all that is happening with the assumption that SNAC is applicable whenever the optimal control equation is explicitly or rather symbolically solvable for control in terms of state and co-state. That you should not forget actually. And if you have quadratic cost function and control affine system dynamics, then this condition is always valid actually. Okay. Just remember that. So, reference sense, again I go back that okay, these two references are the backbone of this particular lecture actually. One is a chapter on a particular handbook, the other one is our own paper actually. See more on that. Alright, thanks for attention actually.